Yes. Okay, he was playing exactly some details about his PhD. And afterwards, he will speak about his postdoc project. And we welcome you. I think this is the first formal introduction, right? Okay.
And well, today I want to tell you about this project we have with Barcelona in order to build a multiparametric biosensor for studying the adhesion of erythrocytes to the surface of blood vessels. Because this phenomena of adhesion of erythrocytes to the blood vessels is present in some diseases and is related to the most severe forms of these diseases. So this project was what I have done in my PhD in order to present myself and say what I'm expert of, in which field I have some expertise. So in my PhD I work with proteins, and particularly membrane proteins. And among these membrane proteins there is a family of proteins called T-type ATPases. And the members of the family share the same function. They transport ions or lipids from one side of the membrane to the other. And that transport is coupled to ATP hydrolysis. Among these proteins, there is this one called the plasma membrane calcium ATPase, or PMCA, which is a protein that transports calcium from the cytoplasm to the extracellular space. And it's very important for cells. In fact, it has been proven that this protein is essential for many biological processes, like the sense of hearing. And also it has been related to many pathological conditions like hypertension and cancer. And also this protein has some particular characteristics. It has several regulation mechanisms. For example, it has this C-terminal domain, which normally is interacting with the rest of the protein and inhibiting the protein. So the protein normally is auto-inhibited by this C-terminal domain. And in presence of camoglin, which is another protein, this protein can bind to this C-terminal domain and activate the protein. But this mechanism of activation, as well as other mechanisms of activation of this protein, are not fully understood. So because of its biological relevance and its mechanisms of regulation that are not fully understood, that were the reasons that motivated us to study this protein. And what is interesting about P-type ATPases is that they transport ions with a complex reaction site. And enormous progresses have been achieved in the last 15 years, because one member of this family, the cytoplasmic reticulum calcium ATPase, or SERCA, will be crystallized in different steps of this reaction cycle. So I'm showing here a video that I made morphing different PDB structures of this protein in each step of the reaction cycle. And you might see that during some time the protein is phosphorylated. And studying the phosphorylated states in these proteins is very difficult because these proteins can spontaneously desphosphorilate. But fortunately, there are these fluoride complexes that can bind to proteins and mimic the presence of a phosphate that is interacting with the protein. So it has been seen that with beryllium fluoride, it's possible to stabilize this protein in a conformation that is very similar to the conformation the protein has when it has the phosphate covalently bound. And for example, with aluminum fluoride, it is possible to stabilize the protein in a conformation that is very similar to the transition state of the dephosphorylation reaction. So by using these complexes, the phosphorylation and dephosphorylation reactions of this protein could be studied. So in my PhD thesis, I used these complexes to stabilize the PMCA protein in the phosphorylated intermediate and study its structure. So our main hypothesis when we began this work was that beryllium, aluminum, and magnesium fluoride complexes can lead this protein, the PMCA, to analogs of the phosphorylated state. And if this hypothesis is true, we could then study the different effects of some variables like the calcium concentration that could give us information about which kind of intermediates these complexes can stabilize. Because there is, if you saw in the previous slide, there is more than one phosphorylated state of the protein. And then when the protein is stabilized in this phosphorylated state, we can study the structure of these intermediates by looking at some techniques that can give information about the conformation and changes in the transmembrane region of the protein and also in the cytoplasmic domain. And finally, we would like to integrate all this information with this already known in B-type APIs, in this mechanism of function that I showed you before. So first we started working with purified preparation of the protein, and which is obtained for human blood. And what we did first is to measure the calcium-ATPase activity of the protein, which is the ability of the protein to hydrolyze ATP in presence of calcium, which is its physiological transport activity. And we saw that these chloride complexes are inhibitors of the calcium-ATPase activity of the protein. And we expected this result because these complexes could bind to the phosphorylation site, preventing that the protein could complete its reaction site. So what we did is to measure the inhibition of calcium-ATPase activity at different fluoride and cation concentrations, in order to know which were the best conditions to bind these complexes to PNCA, because we had to ensemble these complexes in the medium of the enzyme. And we also, by looking at this data and comparing with the concentration of different species of these chloride complexes, we could determine that these species were the ones that binds to the protein. Particularly in the case of aluminum fluoride, the aluminum tetrafluoride is the complex species that binds to the protein. In the case of beryllium, it's beryllium trifluoride. But in the case of magnesium fluoride, we couldn't determine which complex binds to the enzyme. But in our p-type ATPases, the complex is magnesium tetrafluoride. So we calculate that this is the complex that binds to the protein. And we also characterize this inhibition, and we saw that it's a slow reversible inhibition. And it takes several minutes to dissociate these complexes that are bound to the protein. So when these complexes bind, they form a stable, strong binding to the protein, and it takes several minutes to dissociate this inhibitor from the protein. And we also studied the influence of calcium concentration on this inhibition. So what we did is to measure the calcium-ATPase activity at different calcium concentrations, and also we measured the activity of the protein that does not require calcium. And by doing it, we can study the influence of calcium on the binding of these complexes. And what I'm showing here is the apparent inhibitory constant of these complexes, which is the concentration of complex that leads the activity to a halt, that inhibits the activity of the protein to a halt. So you can see that aluminum fluoride inhibition does not depend on calcium concentration. So we can postulate that this complex can stabilize both these intermediates of the protein, both E1P and E2P conformations. Because in E1P, the protein can bind at the same time calcium and this fluoride complex. In the case of beryllium fluoride, we saw that the inhibition strongly depends on the calcium concentration, and it's some competition between calcium concentration and the beryllium binding to the protein. So that means that both calcium and beryllium fluoride cannot bind to the protein at the same time. And that means that you can only stabilize this kind of complex, these intermediates in the PNCA with this complex. And finally, we also studied the magnesium fluoride, but we couldn't determine which intermediate this complex stabilized. But based on our data, we can say that it's something intermediate between E2 and E2P. So once we know what kind of complexes what kind of intermediates these complexes stabilize, we study the structure of the protein. And one technique we use is labeling with photoactivatable groups. And a photoactivatable group is this kind of molecule that has a photoactivatable group like this diacerin there. Then when this group absorbs UV light, it reacts and can bind covalently to organic molecules that are in the nerve environment of this group. So you can label a protein with this group on its surface. And these groups has often a radioactive isotope in order to quantify the labeling with this group. In this case, the group I used is very hydrophobic, so it goes in the membrane or in the detergent micelles, and can label membrane proteins in their transmembrane region, the region that's inside the membrane. And what we saw, we did several experiments. We labeled the circa protein I showed you before in different conformations. And we looked at the crystal structures of these conformations and measured the exposed area into the bilayer, I mean the area inside the membrane. And seems to be some correlation between the labeling with the group and the area exposed in the bilayer. So the labeling with this probe could detect conformational changes in the transmembrane region of membrane proteins, and can also give information about the area exposed into the bilayer. So then we labeled the PMCA protein, and we saw that the most important change happens when this protein is activated with catmongolin. And in that case, we see a less labeling with this probe. So then we label the protein in presence of these chloride complexes, when the protein binds these chloride complexes. And we saw that there are no significant changes between the protein which is bound to fluoride complex or not bound to fluoride complex. So these complexes do not cause an important conformational change in the transmembrane region, at least detectable with this photoactivatable probe. Well, when the protein is in an analogous of this phosphorylated state, I mean when it's bound to these complexes, camolin can bind and produce its conformational change, which means that the binding of camolin, that is to activation of the protein, is independent of the phosphorylation state of the protein. So we could detect these conformational changes, and also we studied the cytoplasmic domains of this protein using this molecule, eosin. This molecule binds to the ATP binding site of this protein and can give information about the environment of the site where the ATP binds. And I characterize the interaction of this group with the protein, so that and characterize this interaction in different conformations of the protein. So in presence of the protein, the group has more fluorescence and more fluorescence emission. But when the protein is in a phosphorylated conformation or has bound these complexes, you can see that the group binds with the same affinity to the protein, but the fluorescence of the complex between the protein and the group is less because of this conformational change that these fluoride complexes induce in the protein. So by measuring the intensity of fluorescence, we can measure this change that is caused by the binding of fluoride complexes. So we saw that when the fluoride complex binds to the protein, it binds in a very slow way, and you can see here, and the magnitude of the fluorescence change and the kinetics of this change depends on the concentration of the fluoride complex. So what we did is to fit this equation to the fluorescence data and obtain the kinetic parameters. And that allows us to propose a model of how these fluoride complexes can bind to PMCA and stabilize this fluoride complex. And also we wanted to study further what means that the fluorescence of this group bound to the protein decreases when the protein binds fluoride complexes. So we employ another group which is called TMP-ATP, which is also a fluorescent group that binds to the ATP binding site of the protein. And the advantage of this group is it has been crystallized in Cerca in different conformations. So when the group is bound to Cerca in the ATP binding site, and Cerca binds beryllium fluoride, the fluorescence emission of this group increases a lot. And this is because the ATP binding site gets more compact and excludes water from this site. It forms a very compact binding pocket for the group when the protein is bound to this complex. And this explains why the quantum yield of this group increases a lot when the protein is phosphorylated or bound to this complex. So in the case of PMCA, we saw that the same result as before. The fluorescence of this group decreases when the protein binds fluoride complexes. And that means that these two proteins behave very differently in the ATP binding site. And in fact, PMCA probably what is happening is that the ATP binding site is more exposed to solvent, so water can enter in the ATP binding site and reduce the quantum yield of this group bound to the protein. So this is what I have said now, and the main conclusions of perhaps a summary of my thesis is that these fluoride complexes can bind to PMCA and stabilize this protein in different analogues of the phosphorylated intermediates. And the phosphorylation of the protein produces a conformational change in the nucleotide binding site, which is this domain in green, where it is the ATP binding site. So when the protein phosphorylates, this domain tilts and exposes the ATP binding site to solvent, and that explains why it's more water and the group binding here has less quantum yield. And finally, we also detect this conformational change because of activation of the protein. And we explain this conformational change that the C-terminal domain that is inhibiting the protein goes away from the bilayer when it's bound to common. And that explains why in the transmembrane domain is less labeling with photoactivatable groups when the protein is activated. So this is a summary of what I have done in my PhD. And I hope that my expertise working with proteins could help in this new project we are starting with Dr. Diego Fracharot. So this project is born as a collaboration